So let's see that famous rank nullity theorem. So remember the CR decomposition we obtained. Uh, we have many facts actually from that CR decomposition, although it was not rigorously proved. You could prove that, well, you see how it was generic enough to constitute something that it was just observations actually. Okay. So what we got? The number of columns in A. That's what we started with. Okay, A is still our matrix that has n rows and p columns. So it starts from Rp. You can consider it as a map from Rp and with values in Rn. Okay, so that number of columns was obviously equal to the number of pivots plus the number of free variables. So that's something you obtained just when you were already last year computing the row echelon matrix. Okay, and the reduced row echelon matrix. So now we know we are able to interpret this in terms of dimension of spaces. So that's the dimension of the row space. Okay, number of pivot lines, pivot rows, and the remaining rows in your matrix is going to be the dimension of the null space. Okay, so and we saw that the dimension of the row space was equal to the dimension of the column space. This is something we really obtained from the CR decomposition, that one, and so plus again the dimension of the null space. So what does that give us? This is equal to what's called the rank, dimension of the column space, plus the nullity, dimension of the null space. So here we are, the rank nullity theorem. So we have our matrix. So how can we state that? The dimension of the domain of A, so that's the RP we have here, is going to be equal to the sum of the dimension of the column space plus the dimension of the null space, the rank of A plus the nullity of A. It seems a bit, I don't know, maybe strange, but we will see that it has a lot of nice implications and a lot of nice applications, and this is something that we will see also when we don't talk about matrices, but more general linear maps. Okay, first thing, well, you all know that this is, when we consider this as this matrix as a map, it means that we can take X in Rp and it gives you Ax that belongs to Rn. So let's say Ax equal to B. And this is often the kind of equations that we want to solve. Okay, all right, so let's see. Solving equations Ix equal to B, how can we reinterpret that with the new knowledge that we've acquired? All right, so given B in Rn, obviously X should belong to Rp. Is that solvable? First of all, obviously, if B is not in your column space, then you have no solutions. Okay, that's pretty obvious. We've already stated that. And if B belongs to your column space, you have at least one solution. Let's call that solution x0. Okay. Could you have any other solutions? Why not? Okay. So let's assume you've got two solutions, x0 and x. Okay. Let's assume that for the same B, you've got ax0 is equal to B and ax is equal to B also. Okay, let's take one minus the other, all right? So I'm trying to do it in the same order as here. So that's sorry, that's going to be ax minus ax0 is equal to b minus b. That's equal to the 0 of Rn, okay? You don't have to always put the index, but I think it's a good idea to take this habit so that you are really conscious every time you do this you write this kind of equations, what kind of items you are manipulating. Okay, I can factor with a. Okay, x minus x0. That's keeping the right properties of the matrix vector multiplication. So let's now interpret this. Ax minus x0 is equal to the 0 of Rn. What does it mean? We know that this means that x minus x0 belongs to the null space of A. Okay, so if ever the null space of A is more than just the zero element, then you can have plenty of solutions. Okay? Take one specific solution, x0, and add anything that comes from the null space. Okay? Then that's going to be still a solution, right? So if you've got some specific x0 such that a x0 is equal to b, take anything, any u that belongs to the null space, then you've got a of x plus x0 plus u is going to be a of x0 plus a of u, and so that's just going to be b plus 0, so b. Okay, so you've got an infinity of solutions, right? So if b belongs to the column space and the null space is not reduced to 0, you've got an infinity of solutions to your equation ax is equal to b. All right, so this is summed up in, if the dimension of the null space is greater or equal to 1, then you've got an infinity of solutions. Specific cases, if the rank of A is equal to n, so that means that the column space is the whole of the image space, all of Rn, then vocabulary point, we say that A is full rank, and then we know that for all y in Rn, I can solve this equation, right? Think why this is related to surjectivity. Well, it's obvious. Okay. Conversely, if the null space is reduced to the 0 element, okay, then there will be at most one solution to ax is equal to b, right? So ask yourself why, but it should be pretty obvious from what's preceding, right? If A is full rank, but the okay, even if A is not full rank, right? So try to think how the fact that the null space is reduced to only the 0 element is equal to injectivity. Okay, so maybe do that thinking. Try to think about that now and later. Right? These are very important ideas. Maybe we're not going to use them right now, but it should carve a path in your mind, okay? And finally, if you've got a square matrix, n is equal to p, and A is both full rank and the null space is dimension 0, then A is invertible. Well, it has the two above properties going to be injective and surjective, and think why the rank nullity theorem is important there. Okay, good.